Hello guys, welcome back to my channel Gamma Di Gamma. So, I hope you liked the past couple of videos. They were about geometry, but now I said let's do something interesting, let's do something involving integrals. So because of that, I have the video for you. Now this is not the hardest of integrals that we're going to do, but it is still pretty interesting because I will present two methods. One is the direct easy approach, which I'm going to start now, and the other one is actually the indirect approach. And then I'm going to give you an application in the end of how we can use this integral or where this integral is actually found. So first of all, the integral is 0 to pi dx over a squared minus 2ab times cosine of x plus b squared. And now, for those of you who have been following me for a while, might know how to do this kind of integral. It's kind of simple. Let us first say that a is greater than 0 and b is also greater than 0. Okay. Well, first what we do is we actually use the half angle identities on this entire thing. So we can simplify a few things. So first of all, we can multiply, or rather actually expand. So we're going to have this factor, and then we'll have the a squared plus b squared factor. Okay, and then we'll have a negative 2ab. And now the cosine will be expressed as 1 minus tan squared x by 2 using an identity, divided by 1 plus tan squared x by 2. And we can always simplify this going ahead to give us integral 0 to pi dx times secant squared x by 2 divided by, we can cross multiply this, a squared plus b squared times 1 plus tangent squared x by 2 negative 2ab, and we'll have the 1 minus tan squared x by 2 factor in there like that. Okay, and then we can do a substitution. Let's say u is, maybe let me use a different color, otherwise it will be hard to spot it once we go back. So then I will be, the integral will be 2 from 0 to infinity, because tan of pi over 2 is infinity, du over a squared plus b squared times 1 plus u squared minus 2ab 1 minus u squared. Fine, we can respect that. And now we can simplify this even further. So we can group the u squared terms together. A squared plus 2ab plus b squared plus a squared minus 2ab plus b squared. Now, I think all of my viewers have taken the first algebra sequence, so they know what these quantities here are, this quantity in the bracket and this quantity outside. They both know how to simplify. We will have u squared times a plus b whole square plus a minus b whole square. Now, what's going to matter here is actually what substitution we make. So if, and I will change the color now. If a is greater than b, then the substitution will be a minus b over a plus b times tan theta. We know we have to do a trigonometric substitution here. Question is, this extra condition is going to pop up. Why? Because, well, if we try to reverse this, it's going to be arctan of a plus b over a minus b times u. Now we know that u is actually positive because, you know, u is going from 0 to infinity, right? And arctan, well, it's an odd function in the sense, if we sketch it out, it's going to look something like this. I think that wasn't such a good job. Okay, and this is like negative pi over 2 and like pi over 2, basically. That's arctan function. And we know arctan function is odd. So if you feed it a negative input, you'll get, you know, the output just multiplied by a minus sign. So theta would have to go from negative pi over to you know, 0. But if we like sort of fix one thing in our head, that we want the integral from 0 to pi over 2 and we don't want any minus pi over 2 to 0, then, you know, this substitution makes more sense, because now if a is greater than b, then a minus b is positive, and then entire thing inside the arctan argument is all positive, and then theta is, you know, defined on the positive 0 to pi over 2. If that's not the case, then instead of actually switching this into the bounds of integration, what we can do is we can just sort of, you know, make that decision from the substitution step itself. So what I mean is, if b is greater than a, make the substitution b minus a over a plus b times tan theta, so that, you know, when you reverse this out, you're going to get an arctan of a plus b over b minus a times u. So that, you know, again, because b is greater than a now, the argument is still positive, and then we don't have to sort of flip the bounds, or, you know, make the bounds go from minus pi over 2 to pi over 2. So finally, after all of this, you know, let's say we work with this, the first substitution, because the other one will actually follow with a similar set of steps. We will have a minus b over a plus b secant squared theta, and I think I'm running out of space a little bit on that side, d theta divided by a minus b squared secant squared theta. And we will get out of all of this, we'll see some factors cancel out, pi over a squared minus b squared. And then, you know, again, if we do similar set of steps for the yellow substitution on the left side, it will give us pi over b squared minus a squared. No prizes for guessing that. That's wonderful. We've solved the problem, but again, you might say this is probably the easiest integral I've done for a long time. Well, here's another result, because while we're at it, and I will still not answer your question of why we're doing it now. Perhaps the second bit of solving this integral with a different method will convince you why I made this video, or maybe the application will, if you're more application physics oriented. Pi over a squared minus 1 That is another, this is another result you get for free from this, from solving this integral. And actually, this is a pretty nice result, I think. If you don't know, you should know. It's a very neat, handy formula. Now again, let's go to the application. Sorry, I mean let's go to the second method of solving this, namely by the series. Now for this, we can't really know, or we can do some rough work beforehand to sort of determine what series there is that will give us this integral. Thing is, you'll have to sort of work with a series that's kind of given to you. Think of it as some mathematician dreamed of this method, and now we're just confirming the mathematician's method and confirming that it works. Okay, that's b over a now. This method we are assuming without loss of generality, and you will see why in the end. So first of all, if you have to solve this, we can start by splitting the cosine up like that. We've done this probably 50 times already. If you've been on my channel, you've seen me go through this. Now we can collect the terms with the common power of k. So we will have b over a e to the ix, the entire thing raised to k, divided by 2, plus b over a e to the minus x to the k all over 2. Now we want this series to converge, right? Because otherwise the infinite sum will blow up. So let's say the condition we require for convergence is that this common ratio, this thing inside this bracket, has to be less than 1. So when we impose that for both of them, we have b over a e to the plus minus ix, that's combining both of them, has to be less than 1. Well, if we take the complex magnitude, and we will have to, because we have a complex number right here, e to the ix is a complex number, we will actually end up with the condition b over a is less than 1. And since b and a are both positive, I'm just removing the absolute value or the magnitude here to give us b is less than a. Okay, that's the condition we have. And if we wanted the other condition, that a is less than b, we'll just have to flip the a and b from the original setup here. And that's why I said without loss of generality, because we can just replace b with an a and a with the b. Okay, so we're going to get, using the infinite geometric series formula, a over a minus b times e to the ix plus 1/2 a over a minus b e to the negative ix. We can simplify. Again, the algebra I'm going to skip is just take a common denominator. 2a squared minus 2ab cosine of x divided by a squared minus 2ab cosine of x plus b squared. And now you may start to see the denominator that we had in the original integral pop up right here. The numerator is a little bothersome, but we will work through that right now. So a squared minus ab cos x divided by a squared minus 2ab cosine of x plus b squared. Now if we subtract, if we add minus 1 to 2 times the series that we had, minus 1 2 times the series we had to infinity cosine kx, you'll see that the numerator actually cancels out because we have my negative a squared plus 2ab cos x plus 2a squared minus 2ab cosine x divided by, well, the denominator is the same. So you see all the x dependence in the numerator vanishes. We get a squared minus b squared divided by that denominator. All equal to, well, this thing here. Now we can just pull the zeroth k equals 0 term out. So that will be 1 because, you know, anything raised to power 0 is 1. Cosine of 0 is 1. So we'll have 2 minus 1 is 1. So we'll have 1. Plus now the sum will go from k equals 1 to infinity because we took the 0 term away. There should be a 2 there. Let me just move this so that I have a little more space. Cosine kx, like that. Okay, perfect. Now all we can do is just integrate both sides, right? So integrate, with respect to x, obviously, from, well, 0 to pi, because that was the original integral. So when we do that, we get a pi factor from the 1 here, and the cosine integral from 0 to pi will be, the antiderivative will be a sine, and then sine from 0 to pi will always be 0 if you evaluate the upper and lower bounds. Again, I'm gonna skip that, it's easy. So you get a pi, and then you get an a squared minus b squared, and then the rest of this, because those are just those guys in the numerator are constants, you can pull them out, and the rest of it, 1 over this denominator is just the integral that we had. So that's I. So then we get I is a squared minus b squared in the denominator, and then multiplied by the pi in the numerator. And then again, as I said, we can just replace the role of b and a, and then the condition will flip as well. This condition will flip as well if we change the roles of a and b, and also this b over a will become an a over b, and then likewise this a squared minus b squared will become a b squared minus a squared, and that basically reflects the fact that this integral is always positive. I mean, we could have proven from before that this integral would always be positive. I mean, one way of doing it is that, again, now this is just a kind of a digression, like a tangent, is if you have, the integral, well, take the absolute value. We know that's greater than or equal to this, right? Just the integrand with the, the cosine removed. The cosine's bounded. Or I think I should, that instead of, it's a plus b squared. So yeah, when the, the cosine actually takes the value minus 1, that will be a lower bound, and then that we can integrate to be pi over a plus b square, and all of this is positive for ab positive, and again, even if ab weren't positive, the square will make it positive. So that's another way of proving that this thing is maybe we can remove this. Yeah, that this thing is always positive. Okay, now it's time to actually move on to the applications of this. So one application is, imagine you have a setup like this. Let's see. That's kind of horrible. I will try again. Okay, hand drawn is better. So if we have a setup like this, so assume this is like a semicircle line curve that is charged. It's a linear charge density. And say we're trying to find the, the electric field at some point. So, yep, this is an application in electrostatics. So yeah, nice for all those people who guessed it. Say this is point R. Right, and then the observation point is different actually. It's not at the center of this object. To make things more general, more interesting, maybe let's say the point observation is here. So, we have that the vector from the observation point to that point on the charge. Let's call that R prime. You may have also seen italicized R for that vector if you follow textbooks like Griffiths, for example. But again, this is just a stylistic choice. I should choose a different, more distinct color. And then let's say the vector from, the center of this object to O is given by R, capital R. Let's define this angle here as theta. Now we know from basic, calculations that capital R plus R prime is R. So R prime vector is just R minus R. Now if we talk about the magnitude of this guy, R prime, is going to be square root of R squared minus 2RR cosine theta plus R squared. Hey, doesn't this kind of look like the, the integrand of the integral we had before, except, remove the square root maybe? Well, yes, it does, it almost has that form. And that's where the, the sort of the application is going to pop in, because, and okay, maybe let me make this clear. For all those people who are wondering where this formula for the magnitude of like the difference of two vectors comes from, it's, you can say it's the cosine law, or you can say it's the law of the parallelogram law of vector addition. But just, because we have a negative sort of vector, we get a negative cosine to account for the change in orientation. Okay, so we will now have to measure the electric field, which was given by kq over r squared. Now, we have like a continuous charge distribution. So we have k, where k is the Coulomb's constant. Let me make that clear, which is 1 over 4 pi epsilon naught. Let's just keep it a constant. K lambda dl, where lambda is the linear charge density, r prime squared. Now we just have to set up the integral. So we had a k lambda, our constants come out. Integral from 0 to pi divided by, now r squared is just, we remove the square root. So we have r squared minus 2r capital R cos theta plus r squared. And now this is very simple. This is very much like the integral we had before. The only thing we need to really remember is that capital R is greater than small r, just because of the way the diagram was. That the observation point was actually, farther off than the radius of this object. Otherwise, the observation point would have just been on top of the surface of this charged object, or even inside. So when we do that, we actually see that the electric field becomes k lambda pi r, because r is a constant, divided by r squared minus r squared. Fair enough. What's interesting and what physicists do all the time is see the limit as r goes to infinity of the electric field, and that indeed vanishes. Let's say the electric field as a function of radius r, because r is the only thing that's changing. R is the because when we're integrating this, really, that's the only thing that's changing. The observation point is, as it is now. Let's say the radius of this object goes to infinity. Well, that would mean that this observation point here would effectively be located at infinity, right? So so my intuition tells me that the electric field acting at that observation point, which will effectively be at infinity because of this infinite radius r, and we also know that capital R is always greater than the small r, so that means this is definitely at infinity if small r goes to infinity. So my intuition tells me electric field is 0 because electric field decays at infinity. And indeed, that is exactly what is happening when I take the limit for smaller r goes to infinity, or if I consider this as a function of capital R, we know definitely that this goes to infinity because that is really taking the observation point to infinity. That is really taking the observation point to infinity. In the first case, it was effectively taking the observation point to infinity. So yeah, that agrees with our intuitions, and now we sort of have a use for the integrals that we usually calculate, and I think this is pretty nice. This is pretty neat. I hope you liked the video. I hope this wasn't something that you don't want to see. If you don't want to see something like this, please let me know in the comment section, or somewhere else in the community post or something. And if you like it, let me know as well, because I appreciate your feedback. If you have any questions, let me know in the comment section. Peace out. Stay safe. Keep doing math. Share this video if you like it. And see you next time.